Okay, so in this course, this is the first workshop as I told you earlier. And in this problem, we are going to solve the laminar flow in a pipe at Reynolds number is equal to 100. And also you validate the result with the analytical solution. And this is the description of this whole workshop. And here is the problem description that we are going to solve the problem at the Reynolds number is equal to 100. And definition wise, we can see Reynolds number is equal to rho v d upon mu. We will see this thing why this formula is there. And first of all, you can see that you can have the application of pipe flow in many areas. For example, the transportation of the oil, transportation of the gas, transportation of the water, and also inside the many industries like in the power plant. And by definition, the flow it will behave as a laminar when the Reynolds number is less than 2300, and turbulent when Reynolds number is greater than 4000, and in between the flow is a mix of laminar and turbulent. That is the transitional flow. Here you can see that initially the flow looks like a laminar, and here flow is going through the transitional phase, and here you can see the flow is fully turbulent. And the backside of the downstream of the board, you can see is a very good example of the turbulent flow. Okay, now this is the point that we can derive the formula from the very basic principles for Reynolds number. The Reynolds number is a ratio of inertial forces, that is because of the momentum, like the Newton's second law, and the viscous forces, Newton's law of viscosity. So this is M into A, and this is shearing stress is equal to mu du by dy. Okay, so the inertial force is simply a mass into acceleration, and we can write down the density. This is density as a mass upon volume, and from here we can write down the mass is equal to density into volume. So put this formula over here, you get the initial force is equal to rho into volume into velocity upon time. Acceleration is the velocity per unit time. And now I can take this time on the denominator for the volume. This will be volume flow rate. And this is defined by the Q, and this is equal to area into velocity. So now we have the density, and the volume can be can be written as the, so this is the area into length, and length upon time is equal to velocity. So we can write down this one as a rho, and this one as the area into velocity and into velocity. Okay, so this will become the rho times area times velocity square, and the shear force we can get from Newton's law of viscosity, and that's equal to the shear stress into area. And the shear stress is we defined by the viscosity into the velocity gradient in the normal direction. So we can have this form. So now you can see that this area will remain same, which is the area. The mu will be same as a mu, and for the complete geometry, this du will be a velocity, and this dy will be a length. Okay, so we can write down the mu v upon L into area. Now put these two expressions, which are this one and this one, in this formula. So we get the rho a v square upon mu v L upon a. So v will be cancelled one time, area will be cancelled out. So we will get the length will be on in the numerator. So this will be rho v into L, and divided by viscosity. And this length is basically length is something, any dimension that has the in SI system is something that has the between the 2 points. So length can be now it's not strictly to width or length or the height. This can be the length of the diameter. So any dimension that characterizes the flow, or this defines the characteristics of the flow, is the dimension over here, the length dimension. So for pipe flow, the diameter is the important dimension. That's why we replace the length by the diameter. For aerofoil, this will be chord length. And similarly, if we are solving the backward facing step, then this height, the step height, might be the important factor. So you will replace the D with the H naught. Okay, so now in terms of Reynolds number, as I told you earlier, the Reynolds number is less than 2300 flows laminar, and all the particles, they will be moving in a laminar without any disturbance. If there is some disturbance, that will be damped very quickly because of the viscosity, as the viscosity is dominating there. And then we have the some intermittent bursts of turbulence that are continuously being injected to flow. That is the transitional flow. And but once the flow is fully disturbed, then this flow is turbulent, and the S is number. It's when the Reynolds number is greater than 4000. So you can see the flow here is the laminar, but once it is even the Reynolds number is not changing, but as it expands, it gets disturbance, and the flow will become a turbulent. So initially laminar flow, then transitional, and then the fully turbulent flow. Again the same thing here. Okay, but this criteria is different for external flows. Okay, turbulent flow criteria for, I should write down here the external flows, like the flow over aircraft. So for this, the one cutoff number is Reynolds number is greater than 0.5 million. This is along the a surface, like a flat plate, aerofoil, the aircraft fuselage, aircraft wing. But the more accurate definition of the flow is in the laminar, turbulent, or the transitional. So this is the cutoff number. So anything greater than the 500K is the turbulent flow, less than this number is the laminar flow. But this is not a real case. The real case is that the flow from 1 to 10 power 5 to 3 to 10 power 6 is a transitional. And any Reynolds number less than this one is a laminar. And any Reynolds number greater than this number is a turbulent. But this is only true for surfaces without the lot of height or the thickness. But around the obstacle, like the pole or the circular cylinder, the range is 20,000 when the flow will become the turbulent. And other factors will also affect the flow to become turbulent very early. For example, the free stream turbulence, which is free stream turbulence is if I draw this velocity on some point like this, and let's say this is velocity I am monitoring over here. Okay, so this is the time here, and this is the velocity. So this velocity right now is a function of time. So you will see that this will be disturbance there. Okay, so average value will denote the U average, and any fluctuations like this one, this is the U bar, is the change of the velocity from the mean value. Overall, this graph shows the at any point, this is the instantaneous velocity, this is the U of the t. Okay, so now we can convert this velocity into two components. One is the average velocity, second is the U bar, that is the fluctuation in the velocity. So we can write down the ut as U mean plus the fluctuations, U bar. So we define the turbulent intensity, that is the Tu, is equal to U bar upon U comma divided by U bar. So now what does it mean? So I will explain this thing, that this means that, for example, if my average velocity is equal to 20 meter per second, okay, and the fluctuations we are experiencing is a 2. So that is the from mean value to the here. And we are assuming that these fluctuations are same on the both sides of the average velocity. That is not true in the real sense, but for the purpose of analysis, we can assume that these fluctuations are equal on the both sides over the mean value. So now this is the 20 meter per second, and the fluctuations are equal to 2 meter per second. So if we divide this one, this will be the 1 upon 10. This is equal to now 10%. So it means that we have the fluctuations from the mean value are 10% of the mean value. This is what is the free stream turbulence or turbulent intensity denotes. Surface condition also will also determine that the flow will become turbulent or not. Definitely, if the surface is rough, then the flow will become turbulent very early. And there are the many other things that can make the flow disturb. So you can also, for example, this is the surface, and flow is flowing over here. You can have some hole here, and you can blow the flow from here, and this will make the flow turbulent. And why we do this thing? Because this will make the flow turbulent, and turbulent flow has a more energy. So this flow will be, if there's some separation, this flow will be attached to the surface. And in a similar way, we can suck the flow. This will also remove the boundary layer from there and the separation from there and make the flow attached, but this will also make the flow turbulent. And other disturbances may be some deliberates, and sometimes there is a wire strip that is attached to the surface, and that is deliberately done to make the flow fully turbulent. And that is to be done because we want to compare our experimental data with the CFD, which is fully turbulent, like the SST or K omega models or K epsilon model, because they are the fully turbulent flows. So in order to compare the results of the turbulence model or validation of the CFD code, the flow, we forcefully make the flow turbulent so that we can compare them easily. And but if the flow, the Reynolds number is less than this range, then you might have to use the transitional model in CFX or Fluent. And there are two models available. One is the gamma theta SST, and one is the KKL omega, and both gives you the better results. Okay, so this is the some work done by some scientists, and this will give you idea that for the circular cylinder we can have the different flow regimes based on Reynolds number. And the flow is fully turbulent when the flow Reynolds number is from 1 to 10 power 6, 1 million to 3 million. And above this value, like 10 power 6 into 6 into 10 power 6 or 10 power 7, the flow is 100% turbulent. Okay? So when Reynolds number is less than 5, this is known as the creeping flow. And in this regime, because the viscosity is so dominating that the flow path line, what is flowing here, this will completely follow the circular cylinder. And even not because of this high curvature, flow will separate, but because the velocity is so low, viscosity is so dominant that the flow will completely follow the geometry. So there will be no separation at all, but now from this 5, or maybe this can extend up to 15. That's why in the second case, when Reynolds number is from 5 to 15 to the 40, we will see that we have the two fixed vortices in the vac region. These are static, and they will be not moving with the flow. So that's why we can solve this flow with the steady state case. So this is a steady state problem. But here you can see that when Reynolds number is 40 to 90, again the flow is completely laminar in the boundary layer, which is here, and also in the vac region, which is here. But the thing is that in this Reynolds number range, the flow is governed by the vac instability. But from 90 to 150, the flow is governed by the vortex shedding. And then from the 150 to 300, the transition range turbulence in the vortex. So flow is now in the transition range in the vortex. But when Reynolds number is from 300 to 310 power 5, the vortex state is a fully turbulent, like this one. It's smaller in the size as compared to this case, but this vortex state is completely turbulent. But here the flow is still laminar in the boundary layer. And when the Reynolds number is 3 into 10 power 5 to 3.5 to 3 into 10 power 6, that is 3.5 million to the 0.3 million, the laminar flow now has undergone to turbulent transition in the boundary layer. But problem is that the wake is now narrower than any other case, but the flow pattern is not available there. So there's no vortex state is there, and this flow is disorganized. Means it's not getting any pattern at all. But once the flow is more than like 3.5 into 10 power 6, the flow is fully turbulent in the vortex state. It is same as this case where we see the vortex state, one common vortex state, but this vortex state is narrower in the size as compared to this one. You can see, but that's following the same pattern here. And also one more thing is that the laminar boundary layer is now changed to the turbulent boundary layer, which is here. So both vortex and boundary layer, they are the turbulent. So comparable case is this one where both wake and boundary layers are the laminar flows. Okay, now we go through some theory of the pipe flow. So the first topic is the entrance length and the fully developed flow. So let me make a new lecture here. So I will explaining on the over here. Okay, so this is about the entrance length and the fully turbulent flow. Fully developed flow. The flow is still laminar. So let me take this picture from here. Okay, so what is happening? So let me draw the one circular cylinder by myself. So this is the case here. So when the flow is approaching the circular cylinder, the flow is uniform at this moment. Okay, so now flow is entering here, and initially what happens is that this wall is a no slip condition. No slip condition. Why? Because if you take a look on this wall on the micro scale, this wall has some small grooves. Okay, like this. You cannot see this one with a naked eye, but if you go to the micro level, you will see this small groove. So what is happening here is that the flow particles will start to stop here. That's known as a no slip condition. And so the flow, because of the surface is, if you take a look on the surface from the like a micro level, the surface is not of the fine finish, but this is rough surface. So that's why the flow will start to stick there, and you will see that velocity will be reducing. And since there is a tendency that if the one particle is slowing down, so because of sharing between the two particles, second particle will also be slowed down. So if the first particle here is having the zero velocity, so second particle might have the reduced velocity as well. So this will impact the third particle, and then again the same behavior will be repeated. So you might see something like this. And finally there is a point when this profile will be like for laminar flow, this will take a parabolic type of the behavior. And now this profile will no longer change. This profile will no longer change, and this is the point where we say that the flow is now fully developed. Means that now its profile now will not be changing. So what does it mean? It means that now this is the location here, this location. So from this point onwards, the flow is fully developed. And in this region, the flow is still developing. So we can call this as a developing region. Okay, so and also we denote this region by the length as the LE, and then this length can be, and there's no limit on this length. This length can be of any value depending on the application. So, but for CFD purposes, for analyzing purpose, definitely we have to provide enough length so that we can analyze the problem there. And so this is the case we have here. Okay. So after this point onwards, the velocity will no longer be changing. and zero velocity will be exactly on the wall, and the shear stress will be maximum at the wall like this, and will be minimum where the velocity is maximum, because velocity maximum shows that the shearing is not affecting the velocity here. Okay, so this is the wall shear stress. On the wall will be wall shear stress, and in between there will be simple shear stress like these points. Okay, so now we can okay, now mathematically what does it mean? This means that now here the velocity is no longer function of an axial component. It's not a function of the length. Its profile only depends on the radius, which is here. Sorry, this half value will be the radius, and completely this will be the diameter. So now this velocity profile is only a function of the u is equal to function of the radius only. This is the definition of the free developed flow when the velocity no longer change, which is already function, which is a function of radius, and the axial component is no more a function of the axial coordinate. So change with respect to x will be 0, but definitely we will have some change with respect to r. And this will denote our shear stress. If we multiply this velocity gradient with the mu, this will be the shear stress. And if you want to find out the shear stress at the wall, that is where this r is equal to capital R. So this is the r coordinate, but here this r is equal to r, and similarly here r is equal to minus r. So this is the point where r is equal to r, and you will get the wall shear stress. Simple. Okay. Now the question is that can we determine this value theoretically? Not theoretically, but they are empirical formulas. Empirical formulas are the formulas which are like done by the people in the lab experiments, and they collected data, and then they put the best fit on the data. So that is known as the correlations. So we have the correlations for this pipe flow. So for laminar flow, this is the formula given here. So let me copy it over on the OneNote. Okay, so for laminar flow, the formula is that the air entrance, this length, okay, this length will decide by ourselves that how much region we need for analyzing the problem. So this is not a problem. This should be done properly. So this is equal to 0.05 into diameter, which is here, and into Reynolds number. Reynolds number, I told you that this is equal to rho v d upon mu. Okay. So, and for turbulent flow, if you are solving turbulent flow, then this formula will be used. But right now we are solving only the laminar flow, and the Reynolds number we are using is equal to 100. So, based on this formula, we can see that this L entrance, LE is equal to 0.05 into diameter into Reynolds number is equal to 100. So I can write down the LE by D. If I take the D on this side, this will be equal to 0.05 into 100 is equal to 5. So what we got is that we got the ratio of the entrance length to the diameter. Now let's assume diameter is equal to 1 meter. And this will give us the idea about entrance length is equal to 5 into 1 is equal to 5 meters, if the units are in the meters. Okay. But what I found is that these empirical formulas are having the lot of deviation for different cases. So to be on the safe side, what I would suggest is that take this length as double the value. So this LE by D. So let's take this value as not the 5, but take it like a 10. Okay. And this length is 10, and diameter is equal to 1. So that definitely this will not make any difference if you put this by D or not. And this length I'm going to take the same, which is 10. So this is also the, let's say, L developed flow. So this is also equal to 10. And because diameter is 1, so this will not make any difference on these values. So overall length will be equal to LE plus LD is equal to 10 plus 10 is equal to 20. Now this value is very accurate, but the question is that if you want to solve the flow for Reynolds number is equal to 200, then these all lengths will be doubled because this directly depends on the Reynolds number. So I would suggest that we take the length as the 40, so that we can solve the different Reynolds number within this geometry also. So that's why we are taking the length as equal to 40 meters, and this length is combination of the entrance length plus the length of the fully developed flow. So the length is this one, and diameter is equal to 1 meter. So we can now write down over here that the length is equal to 40 meter and diameter is equal to 1 meter. So for whole pipe, the L by D ratio is 40. Okay. Okay. Now the next thing they discuss about the next thing. Okay. So the question is that if you are solving the now we have to because we can convert the Cartesian coordinates to cylindrical coordinates for the pipe flow. So this is the continuity equation for the pipe flow, laminar pipe flow. And we are going to prove that the velocity is only function of radial direction, which we have shown, which we have said that this is the point where the flow is fully developed, and in this point, what is going to happen is the flow is the only function of the radial component. So what we have now assumptions? The only velocity we have is in the x direction, that is the ux. The v, which is the velocity in the y direction, is equal to 0, and there is no velocity in the z direction. So this velocity also equal to 0. Number one. Number two is that for the whole circle, there is no variation of the flow along the angular coordinate. Means that theta direction will be 0. So there is no variation of because this value is already 0. So du by d theta is equal to 0. So now only two things are now remaining is that we can have the either this du by dx and the du by the dr. Okay, r is the radial coordinate, theta is the angular coordinate, and x is the axial coordinate, which is along the length. So now only thing is that we have to see that it's a velocity function of x or velocity function of r as a function of both of the variables. Okay, so now let's go there. And as I told you that the velocity in the radial direction is 0, this term will be 0, and the velocity in the here third direction also equal to 0. So we are only having the one derivative, that is this one. So this shows when the value is 0, this means that this ux, sorry, this should be written as a x. So ux is not a function of, because derivative is 0, so ux is not a function of is not equal to function of the axial coordinate. So this means that now the velocity will only be the function of the radial coordinate. This simply tells us this thing. Okay. Okay, now we have the momentum equation for x component, y component, z component in the Cartesian coordinates. So this is the normal stress. Sorry, this is normal stress, but this is shearing stress for the x component, and this is I would say is the body force because of the gravity, and this is a pressure gradient in the pipe or in any application. And this is a convection term, and the first term is the unsteady. They will be directly 0. Similarly, we have the y component and we have the z component. Okay, the red color shows that this is the normal velocity component. The same is true for this one, and this is true over here. Okay, and similarly, we can have the correspondingly we have the cylindrical coordinates. So r component is this one, theta component is this one, and x component or axial component is this one. So we know that in the r component, if you go through this one, the ur is 0, ur is 0, ur is 0, and the theta velocity is 0, ur 0. It means that this whole component is 0, and there is no gravity in the r direction. There is no gravity at all, in fact, and pressure gradient will remain there, but these again components will be 0. So the pressure is not a function of the radial coordinate. Simply this tells us this thing. Okay, And similarly from theta component, these all values will be 0. Similarly here, and this also implies that the velocity gradient is not a function of the theta component as well. So this means that if this is not a function of theta and r, this should be a function of the only x or the x direction. Okay, now we have the z component equation, that is the, write down x component. So now what we have this assumption that u r and u theta are 0. And also we have from the continuity equation that the derivative of uz with respect to the x and with respect to theta is equal to 0. So only thing is that we have this is the x, that we have the derivative with respect to only r. Okay, so that's why we keep this component here, and the pressure gradient in x direction, that is the x direction. So from here we get the governing equation for the pipe flow, laminar pipe flow. And we can write down this equation as the delta B by delta X and take out this value on this side. This will make the this term as a positive. This is a mu 1 upon R partial by partial R into R partial U X by partial R. So now because it's only single derivative, single variable here, so we can write down from the partial derivative to simple derivative. So dp by dx is equal to mu upon r, d by dr, r du x by dr. And the boundary conditions are that at the r is equal to r at this point, the ux is equal to 0. Simply velocity is 0 here. And at r is equal to 0, where the gradient of the velocity is equal to 0. And this is the point where shear is also equal to 0. But velocity will be maximum here. Okay, and similarly we can take the, for the shear stress, we can take the, from this pipe one element here, and one element has the, these forces. One is the shearing stress. And area for shearing stress will be equal to, this is dx. Okay, so for this dx, we can have the dx here, and this one is equal to, now this is circular cylinder. Okay, so now imagine this is the circular strip, and its length will be equal to circumference of the circle, which is equal to 2 pi r. So if you multiply 2 pi r with the length, which is a dx, this will give us the volume. Okay, this will give us the, this will give us the area. So this is the length unit, so this is the area. So area multiplied with the wall shear stress will give us the force at the wall. Okay. So and similarly we can have the pressures. So here the pressure is P and the area is pi r square, cross-section area. And at the distance of dx, the pressure will be added by the dp. Now this can be negative pressure or can be positive pressure, but difference is there. So this pi square, pi r square is the same, and then we have the P plus PdP here. So now you can balance the forces. So this will be negative direction, minus direction here. So you can see minus pi r square into P is the positive quantity, minus pi r square into P plus dP is the like a negative quantity, and minus 2 pi r dx dot w is equal to 0. Now this is not this is a single quantity, because if you have the circular cylinder from the side view, this is the whole surface here. So this is the one value of the shear stress. So now you can solve this value, and you can find out this will be 0 and this will be cancelled out. Okay, so now remaining is that minus pi r square in dp minus 2 pi r dx into tau w, shear stress at the wall. So now we can cancel out the pi, the r, one r from here, one r and the r from here. So remaining values are like a minus r dp is equal to, now this can be written on this side, this will be plus 2 and dx into tau w. So I can write down dp by dx is equal to minus 2 by r into tau w. It means that now I can find out, either I can find out the pressure gradient from the wall shear stress, or I can find out the wall shear stress from the pressure gradient, because the r is the constant. And please keep in mind that dp by dx, this dp by dx is the pressure gradient along this pipe length. Okay, And this value will be negative because the slope of this one will be like this one, because pressure is decreasing along the length. So you will see that pressure will be higher and it will be decreasing like this. Okay, and this linear profile is only true for the fully developed flow. But if the some portion of the pipe is like having the developing flow, then the profile might be here like this. But once the flow is fully developed, then the profile will be linear, and it is defined by the dp by ds. And to make it minus value, basically what we are doing is that we are making the gradient as a positive value. Okay. Okay, now we can, for this small strip, this is the dp, but for the whole pipe, this will be delta p. And difference is, one difference that, second difference that the dp is equal to p2 minus p1, and the dx is equal to x2 minus x1. But delta p will be equal to p1 minus p2. So it means that the delta p will be minus of the dp. Okay. So, and the length is like total length from this point to this point. So this will be minus dp, and divided by length, x will be changed to the length, and minus 2 upon r tau w. So minus sign will be cancelled out, and what we will get is that we will get the dp is delta p is equal to minus, will be positive 2 L by R tau w. So this L by R can be written as the L by D. Okay. So I can put the 2 into L, and R can be written as a D by 2 tau w, and so delta P will be equal to 4 times L by D into tau w. And so this final formula is this one. So this, from this formula, basically we can either find out the wall shear stress from the pressure gradient or the pressure difference, not the pressure gradient but pressure difference, and from the pressure difference we can find out the wall shear stress. Okay, so now this is a pressure drop in the laminar pipe flow. So as the formula is dp by dx is equal to minus 2 upon r tau w, and the tau w is mu du by dr. And because the tau w, this wall shear stress is a constant value. It's a constant value because we have the velocity gradient, which will be constant value for the given function. Mu is a constant, so wall shear stress will be constant, which is over here. Okay. So it means that delta P by delta X also will be a constant value. Okay. And the negative sign in the pressure drop slope shows that the pressure is dropping along the pipe length. It is decreasing, not increasing. And this will also make the value of wall shear stress as a positive quantity. The velocity gradient at the wall also has a negative slope. You can see the slope here is a negative. Positive slope will be look like, 1 minute. Okay, this is a positive slope. Sorry. Shear stress at the center is 0, and slope of the velocity is 0 over there at this point. Okay, so this is the what we have already done, and now I am telling you the pressure drop for the pipe. So I told you that this linear profile is only applicable when the flow is fully developed, which is true for this developing region, this developed region. But for entrance region, the actual profile is like this. Okay. So we can extrapolate this pressure gradient from here, and now this will be like, in the case of CFD, you will get this profile in the blue color. So in order to compare the values with the theoretical formulas for the full pipe length, or you can compare the values of your CFD with the analytical theory only in this region, which is over here. Then you can also compare it very well. But if you want to compare in the full pipe length, then you have to, from the CFD, you have to make it linear, like putting the same slope as here, find the value of pressure at this point 1 and pressure at the point number 2. This will be delta P or dP. And then from the theoretical formulas, which are these ones, you can find out the values and you can compare them directly, like from CFD and from the analytical formulas. Okay, now let me give you idea about these formulas, how these formulas are derived. So I will cover that thing in the next lecture. I will go through these formulas, but for a time being now, we will understand the pressure drop in the pipe. And this is the actual pressure drop from the CFD analysis, which we will be running in this course. And this is the actual one, which is non-linear, you can see in the sum portion here. And this is the linear profile that I fit by putting a straight line and following slope over here. So value I'm getting here, this is going to be equal to the a value that is equal to the linear profile. That is the when we assume the full pipe is like behaving as a fully developed flow. Again, same formula we are using here. The velocity profile that we discussed earlier, that has the parabolic shape, and its equation is like this. The UR is equal to 2U average into 1 minus R square upon R square. This one also we will drive, and also we will see that the U maximum is at the center and its value is twice the two times of the V average. So this twice V average is basically is the U maximum, but we don't put the value U maximum here because we don't have the idea about the U maximum, but we do have the idea about the U average that we are putting at the inlet. That's why we put the formula with this way. And this is underlying velocity. So you can see that this velocity is now, you know that the maximum velocity is going to be at the center. This velocity will be equal to twice the U average. So U average is 1, then this value will be equal to 2. So the thing is that if this is true, so we should be achieving this value at the center. But problem is that because the flow is not fully developed, so in the very beginning when the flow is developing, the everywhere velocity is 1. So that's why you can see that in the beginning of the pipe length, you can see the velocity is 1. But once the flow is developing, you can see velocity changing, and then it is reaching the value of like a 2 here. So this is all about these formulas. Okay, now we are going to drive these formulas one by one. Okay, these are all formulas.